Now, when we use the log function, it's important to know the math. Okay, so if we're considering this here, let's say, log to the 10th power, it'd be decibel to the 10th. So let's take an example of 40 decibels, and we want to find I. What we're going to do is we take it to that power, and so in this case, we have 40, and then we're going to divide both sides by 10. So we have 40 decibels, right, equals 10 log I over I 0. So we'll divide both sides by 10. So we have 4 equals log I over I 0. And then once we do that, we'd take both sides to the 10th power. So it'd be 10 to the 4th, and then you'd have that equal I over I 0 if we take, to the 10th power for both sides. And then yeah, we can do this too. We can calculate the I over I 0 in the log beforehand, or else it may not, correctly do that. So when you're doing that log function, make sure you do that. And then you want to be ready for relative amounts with relative decibel amounts. And so, getting those relative amounts would be important. We'll practice that as well here. All right, so let's try this sample problem. How does the intensity of a car horn at 110 decibels compared to the intensity of a normal conversation? So in this case, what you actually have to do is calculate the intensity of each of these separately, and then we can compare one to the other. In this case here, you have to calculate what is this intensity, then what is this intensity, and we can compare them. So go ahead and do that. And so pause the clip, and then once you've done it, you can hit play to continue and check. All right, so we have the normal conversation versus the car horn. So the car horn, 110 decibels, divide both sides by 10. Then take the value 11 to the 10th power there. So this, 110 divided by 10 will give 11. So 11 equals log I over I 0. So we take both sides to the 10th power, so 10 to the 11th, and then we cross multiply. We'll get 0.1 watts per meter squared. And then for a normal conversation, 50 decibels, we'll have 50 divide both sides by 10. So we have 5 equals log I over I 0, and then we take both sides to the 10th power. So 10 to the 5th equals I over 1 times 10 to the negative 12th. Cross multiply, so the intensity is much, much smaller, right? So 1, 2, 3, 4, 5, 6. That's much smaller than this, right? Much less air being pumped. But, the intensity or the loudness doesn't change nearly as much. And so remember, that's a really important part of seeing this. It's a logarithmic relationship here. So yeah, how many more times? Like a million more times sound. So it's crazy. All right, so we're 3 meters from a speaker, and our decibel reading of loudness is 80 decibels. We want to find out the power of the speaker. So then you're going to do that first. So you're going to calculate the intensity, then you can calculate the power. And then the second part, what would be the decibel reading at 0.5 meters? So again, you have to first figure out what is the objective power of this, right? What is the power of the speaker? And then once you do that, then you can do part 2, because you really have to, the loudness is separate from the intensity. We can't just say, oh, I'm 3 meters away and now I'm only 0.5, and so set up some ratio or something, because this is a logarithmic relationship. So go ahead and pause the clip and go ahead and get the power rating first, and then you can check, and then we'll go from there. So go ahead and calculate the power rating first, and then when you're ready to check, you can hit play to continue. All right, so 80 decibels, and so we'll get 80, divide both sides, 80 divided by 10, 10 to the 8th power, cross multiply, so that's the intensity. We can calculate now the power, so you should have gotten 0.01131 watts is the power of the speaker. So now what I want you to do is figure out the intensity at 0.5 meters. So go ahead and pause the clip and calculate that out, and then we'll compare it to the other one. All right, so there, we should get a intensity of 0.0036. Now what we can do is we can calculate the decibel reading. And so when we place this back into here and we're solving for the decibel reading, we'll get 95.56. So originally we had 80 decibels, and then at 0.5 meters, it only went up a little bit. It only went up to 95. Now the intensity of the sound, you know, is different, right? So 0.5 versus, you know, the other, but yeah, so it's what we have there. So let's go ahead and take a look now at this here. Let's say that the sound intensity of the speaker went up by a factor of 50 when there's misplacement of a microphone that's put too close to the speaker. What's the increase in decibel level? Well, again, here we have, you know, intensity versus decibel level. We have to compartmentalize these, right? So in other words, here we have 50 times the intensity. Are we going to have 50 times the decibel level? Definitely not, right? So we got to figure out, you know, in terms of what would the original decibel level be, and then what would the final be. There's different ways to do this. Why don't you go ahead and pause the clip and see if you can come up with a method to do that. And then when you're ready to check, you can hit play to continue, and you can compare my method with yours there. Okay, so here's the original intensity. I just made up one here, 0.0036 as the original intensity, versus 50 times louder than that would be 0.18. So you could have done any value that you wanted to. You could even have used 1, which would have been, you know, really, really high amount, but that would have been fine. So 0.0036 versus 0.18 watt per meter squared. We have to calculate these separately. So that would be 112.55 decibels, 0.18 watts per meter squared, which would be 50 times the original. And that would be versus what we just found in the last problem. In the last problem, we found it would be 95.56 decibel levels or decibels for that intensity. I'm just carrying that from the last problem. And then versus this, so it only increased by 17 decibels, right? 50 times the intensity, but only increased by 17 decibels. Okay, so when we look at strings, strings are a type of instrument where, you know, you play the string and it's vibrating back and forth and it makes a certain pitch. And so what I like to use is my guitar in class, and we'll draw out the guitar. We'll take a look at, you know, take a look at the string. We'll measure the length of the string, right? And then we'll take a look at the first harmonic. So this string, one of these strings, and this is obviously exaggerated just to see it here. So one of these strings is doing this, and so it's a standing wave, right? And so if we drew the rest of the wave, it would be like this. And so in terms of the fundamental frequency here, the wavelength would equal 2 times L, because the wavelength is, you know, this entire thing here, but the L being the length of the string. And then, you know, the wavelength would be 2 times L to get that. We would also take a look at here. We know V equals frequency times wavelength, right? So if this is here in 2L as the wavelength, then we had V equals frequency times 2L, right? And then if we wanted the frequency, we would divide both sides by 2L. So the frequency of the string would be V over 2L. And so if we knew the length of the string, how many meters it was, and then V being the speed of the waves on the string, and that is a really important point because this is the actual speed of the waves on the string itself. That's the speed of the waves. We would get, you know, what the frequency is, at least with the fundamental frequency, the first harmonic. And so once we set that up, we've got that. Again, V represents the speed on the string, V over 2L, and we can take a look at, you know, what that actual frequency would be. And if we had, let's say, a length of 0.635 meters and a speed of 475 meters per second on there, we could calculate the frequency. And so in this case here, the frequency, the fundamental frequency would be 374.02 hertz. Now, if we look at the second harmonic, on that same string at the same time, it turns out, we also have the second harmonic. And so, yeah, and that's kind of crazy to think about, right? On the same exact string, at the same exact time, we have the superposition. We actually have both harmonics on there. And so the second harmonic being played, in this case, in terms of L, right? L being the length of the string, L is actually the same as the wavelength. And so, L equals the wavelength in this one. So in other words, if we set up that original equation that we just did, but then we have n as the integer in terms of the harmonic, and we put a 2 in there, this being the second harmonic, the 2's are gone, and then we actually get this, right? And so, and which is correct, because V equals frequency times wavelength, right? And so in this case, L is here. So frequency equals V over L. And so therefore, if we have the second harmonic here, we put a 2 in there, the 2's are gone, and then V over L, same thing. And so the second harmonic will be a higher pitch. If we have the same speed, let's say 475 meters per second, and the length of the string is 0.635, we'll get a frequency of 748.03. And it turns out this is twice as high as the fundamental frequency. And so the harmonics are actually multiples of the fundamental. You have the fundamental frequency, which we had, which was half of this. If we did the third harmonic, it would be 3 times the fundamental. Fourth harmonic, 4 times the fundamental. So as we get higher and higher in the harmonics, we get higher and higher frequencies. So with the standing waves that are on the spring there, we have the wavelengths there, and we end up getting the frequency, and this is really what you'd want here. The frequency of n harmonic equals nv over 2L. And so the n is the harmonic number, and we can have any sorts of combinations of those on a given instrument. Even with like a violin string, you could have maybe the first, second, third. Maybe it'll skip a few and have the fifth harmonic, and then skip a few, maybe have the seventh harmonic. Just depends. And so the quality of that instrument, the quality of that sound, the timbre as it's called, is the combination, the superposition of all those different harmonics that we can listen to. So let's go ahead and try this one here. What's the third harmonic for a string that has a length of 0.53 meters, and the speed of the waves on the string is 440 meters per second. So go ahead and pause the clip and give this a shot, and when you're ready to check, you can hit play to continue. All right, so we have the third harmonic, which should actually, my picture is kind of bad here. It should look something like this. An antinode here, an antinode here, an antinode here. V over 2L, and then it's the third harmonic, which should get 1245.28 hertz. So what I'll do in class is I'll have a couple students stand and hold the spring and make the first harmonic starting out. So here's the spring and the first harmonics there, and then I'll be standing in the middle and I'll be holding a block. And so what we're representing is playing harmonics, and we're imagining this being a guitar string. So if I stand in the middle and I block this, the antinode, it kind of kills the first harmonic. But if we do this, right, and I have the students do this next, is draw the second harmonic, which looks something like this. And if I stand in the middle and I block the middle, there's a node there. So these can go freely. And so if I hold my finger there or hold my hand there, it blocks the first harmonic, but it does not block the second harmonic. When they do the third harmonic, which looks like this, the third harmonic gets killed. But then when they do the fourth harmonic, well, let's draw the fourth harmonic over here, which are 2 full waves, like this. The middle is fine too. And so what ends up happening is the fact that if you hold your finger over a guitar string in a very specific spot, you can, and not clamp it down, but just hold it there, you can actually kill some of the intermediate harmonics, and then some of the other ones survive. You can actually get a different pitch. And so what you can do, and if you actually shorten the string, if you shorten L, then L is shorter, you have your frequency gets higher. So that's important to note there. But if you just rest it over the string, you can actually get those harmonics. And in this clip, if you look it up online, this is the instrument, or the musician is clamping down the strings. Sometimes when he clamps down the strings, the L gets smaller, so the frequency gets higher. But sometimes he's just muting some of the higher harmonics, just resting his finger over the strings, and then some of the harmonics survive, and you have a different combination there. Now, as we consider different instruments, and the first one here being the string type instrument, we have strings that are longer and shorter in a piano. And so we know that the longer L is, the lower the frequency. And we can also set the tension as well. And so both of those have a factor, in the kind of pitch that you have. So, these longer strings are going to have a different pitch than, these smaller strings here. And there's little hammers that are located here where they actually hammer onto the string. And when they do that, produce the sound. And so instruments, provide different sounds through different ways. And so, with strings, they're vibrating back and forth. And then, with wind instruments, you have the air going through them. And what's similar with all of them, though, is that you have resonance. You have them shaking at their natural frequency, or frequencies, plural, depending on the kind of instrument. And so, with a stringed instrument, you can pluck the string, strike it,